Okay, so today I'm going to tell you about the future of the universe. It's a remarkable story, really, because it's strange to believe. We all know that, a long time ago, and I'll tell you more about that, how Edwin Hubble discovered the expansion of the universe, although he never really believed it was physically expanding. But in the past decade, we've become completely convinced it's not just expanding, but it's moving faster and faster, accelerating. The distant galaxies are moving faster and faster away from us. So I'd like to tell you a little bit about the story behind that. Okay, so it all begins with Einstein, of course. He developed his theory of general relativity in 1916, theory of gravity. Now, I don't want to bore you with his equations, but what he did was bring in the tensor calculus into cosmology in 1917. And in some sense, this meant that previously, the philosophers and the theologians all had a go at telling us about the beginning of the universe, but suddenly, the tensor calculus is a barrier that only the scientists could really penetrate. And since then, things have changed slightly because I know philosophers who are trained in physics and even theologians too. So things have changed a bit in recent years, but for nearly a century, there was a real division, that scientists dominated our thinking about the beginning of the universe. Anyway, so Einstein was, of course, an amazing person who loved beauty and in many things. He was an accomplished violinist. And in these equations of the tensor calculus, which describe gravity, his new idea was to say that space is curved, and that contains all the effect of gravity, basically. In other words, if gravity were present and there's some, basically bend space, this is an example, so it means the angles of a triangle no longer obey Euclid's theorem. What you learned at school is no longer valid, although it's approximately true, it's no longer actually valid in the universe. Anyway, so what Einstein did was, these are his famous equations about gravity, and he realized that there was a big problem in 1917. It was his first application of his theory of gravity to the universe. He said, let me try to explain where we came from, or why we're here, how we're here. And he realized that the universe he deduced would collapse under gravity unless he did something to stop it, and that would be a disaster, to have an unstable model of the universe. So he introduced a constant, famously known as the cosmological constant, this little thing lambda, which basically stops the universe from collapsing. It's like anti-gravity. So that was Einstein's role in 1917. Okay. And then the next step was taken by another cosmologist who, in fact, was an ordained priest and did his PhD in physics at both in Belgium and at MIT in the US, and then went to California briefly and got very interested in the expanding universe. And he, in fact, found something that Einstein somehow missed completely in his study of the universe. Namely, Einstein just thought in terms of a static universe because everyone around him did at that time in 1917. But he missed a solution to the equations which said it could be expanding. And if it were expanding, there would be no need to introduce that awful arbitrary constant, which was anti-gravity, into his equations. And Lemaitre remarkably found this missing link. Unfortunately, he made the big mistake of publishing in French, and very few people read what he did. So he presented his work in 1927 at a famous conference in Belgium. So his idea was that the universe, in his interpretation of Einstein's theory, began from a very, very small size, in fact, essentially zero size. But there was a beginning, and then it kept on expanding. Anyway, so at this conference with many, many famous physicists, Werner Heisenberg, the founder of the uncertainty principle, Wolfgang Pauli, Erwin Schrödinger, the Schrödinger's cat paradox, etc. Paul Dirac, the great English founder of quantum theory, Max Planck, Einstein in the center, And Lemaitre was there somewhere, a young man who was not in the, with the great people, but he gave his talk. He chats with Einstein. This was taken slightly afterwards, but you get the general impression, who comments on his talk. And Einstein tells him, and it's beautiful in French, but let me read the English anyway, "Your calculations are correct, but your physics is atrocious. This is too much, suggesting a creation." And Lemaitre replied, "The hypothesis of the primeval atom," that was what he talked about at the beginning, "is the antithesis of a supernatural creation." So he was to make a big issue that the theories of relativity predicted a physical beginning for the universe. And I'll explain briefly later on how that did affect our ideas of religion too, and the views. Anyway, so there was a predecessor to this, okay? Alexander Friedman. It's a remarkable international story, actually. So he was a mathematician, and in 1922, at the age of only 35, he also looked at Einstein's equations and found that Einstein had made this elementary mistake of dividing two sides by 0 or something and missed out the equations of the expanding universe. So Friedman was the first person to realize there was this missing thing, an expanding universe was possible, okay, and he published that. Sadly, he died in 1925, very young, okay, and although he had a discussion with Einstein, who simply said he didn't believe it, and first accused Friedman of making a mistake, and finally Friedman said that Einstein had made the mistake, and they agreed on that. But Einstein would not let it go any further. Then his work was simply unknown to the general public until the Belgian came along. And Lemaitre went one step further. He didn't know about Friedman's work. He went one step further. He said, well, not only could the universe be expanding, but he said there are data out there. And these data had been accumulated by Americans, actually. One guy in Arizona called Vesto Slipher, who worked at the Lowell Observatory, named after its benefactor, Percival Lowell, who was the person who first thought he saw canals on Mars. That's another story. They were obviously fallacious. Natural, they were natural ravines, whatever. But Slipher had data on galaxies and measured from their redshifts, their speeds, apparent speeds, and that's plotted, in this direction, velocity. And then he and another American astronomer called Edwin Hubble, more accurately, got the distances to these distant nebulae, or what we call them now galaxies, and found the further away they were, distance, the faster they seemed to be going. And so Lemaitre predicted that the universe was expanding, and even measured from the slope of this line the rate at which they're expanding. As you go further, how much faster things expand. But as I said, Lemaitre made, not the mistake, he published in French, and his work was completely oblivious until an American came along, Edwin Hubble, and in 1929, just 2 years later, he published essentially the same data as Lemaitre, also drew a line through the points, got essentially the same constant for the rate of expansion, and ever since we've called the expansion law Hubble's law, okay? It should really be the Hubble-Lemaitre law, I think. Anyway, so that was 1929. Well, the news spread around the world like wildfire, and Einstein went to the US, and in 1931, he went to see Hubble, who took him up to the telescope on Mount Wilson. And here you see Einstein looking for himself, I assume in this posed picture, not that he could see very much, but he became convinced at this encounter with Hubble that the universe really was expanding, that there was something interesting going on, and this would explain his problem he had with why in a non-expanding universe things would be a disaster unless he introduced this weird cosmological constant, or whatever he called it. Okay, so interesting. So later that year, Einstein went to Oxford, and he got an honorary degree, okay, and gave a talk, and this is on a blackboard that is preserved at the Oxford Museum of Science, from Einstein's talk in which he accepts the expanding universe and goes on to do calculations. Now, the amazing thing is that Einstein, who was a brilliant physicist and mathematician, didn't get it right. There are elementary mistakes in these calculations. You can see them on the blackboard in the Museum of Science in Oxford, in which he gets the density wrong by a factor of 1,000 of the universe, okay, and gets the size wrong and the age wrong, okay. So it's just bad. But the curious thing is, despite the fact that all of this was wrong, in those days, he got away with it because he published in a journal that was not refereed in 1931. And then it was out there for everyone to see, and that was the beginning, really, of the bandwagon of modern cosmology. With Einstein's imprimatur on this, one could hardly go wrong. And then a couple of years later, Einstein and Lemaitre went on a lecture tour to Pasadena, and Einstein heard Lemaitre again give a lecture. So 6 years had passed, and this was Einstein's comment. "This is the most beautiful and satisfactory explanation of creation I have ever listened to." Okay, so Einstein changed his mind. Lemaitre actually wasn't too happy with the use of the word creation, but apart from that, all was well. Einstein was convinced the universe was expanding. Okay, so this was an amazing time in cosmology, because in the years 1929 to 1932, there was a big depression going on, but the Big Bang was literally exploding for the scientists. And these are the people who are sort of immortalized. Hubble really for making the big announcement of the expansion and having it seen by everybody, and Lemaitre, who did the same thing. But then he was an observer, but all these other guys were theorists. There was Einstein, of course. There was Arthur Eddington, an Englishman, William de Sitter, a Dutchman, and Lemaitre. So very international. We have a Dutchman, a German, Englishman, Belgian, and the American, okay? All playing a role. And all of them are immortalized because now we have Hubble's law for the expansion of the universe. We have the universes that these publish, the expanding universes named after them with slightly different properties. There's one we call the Eddington-Lemaitre universe, another one we call the Einstein-de Sitter universe, which is the closest approximation to the actual universe now, in fact. Okay, that one. Okay, so, all right, perhaps even a combination of the two. So it's, a bit of everything, really. But these are the people in those 3 years that somehow lit the touch fire that explained the Big Bang, developed the Big Bang, which wasn't even called the Big Bang in those days, but was queried a bit because it did begin from an arbitrary small radius. People worried about that. But the main point of all this was there was no longer any need for this bizarre thing Einstein added to his equations to stop the universe from collapsing, which he called the cosmological constant. And Einstein, he admits the introduction of the cosmological constant term was the biggest blunder of my life, okay? And that's a quote that you can find. So, the great men can make mistakes, right? But just to show you how this captured the public imagination, here's from a Dutch newspaper, a cartoon. And this is De Sitter. This is lambda, this cosmological constant, okay, blowing up the universe, okay? So things like this very attractive to the newspapers. That's gone on, of course. Here are some more cartoons trying to describe the size of the Big Bang. The only part of the universe which isn't expanding is the budget for this place, right? That's all very timely things. And finally, this is the universe before the Big Bang, okay? So the expansion did help a lot in making it much bigger, and I'll try to explain why. Okay, so let's talk about the origin of the name The Big Bang, okay? So in some sense, these are beautiful words from Lemaitre. Let me read them. The evolution of the world can be compared to a display of fireworks that has just ended. Some few red wisps, ashes and smoke, standing on a well-chilled cinder, we see the slow fading of the suns, and we try to recall the vanished brilliance of the origin of the world. So clearly, this view of a beginning attracted the ire of some people. Fred Hoyle was one of the most outspoken critics, and in a radio broadcast in 1951, he just complained. He invented the name of the Big Bang as a means of sarcasm and said it's an irrational process and can't be described in scientific terms. Okay, and he was very insistent on a rival theory, which we call the steady state theory. Now, in the steady state theory, to avoid having a beginning, he postulated, out of nothing basically, that there was creation out of nothing. Creation everywhere, which replaced the stuff that was expanding. Now, some people think this is as an extreme hypothesis as the very beginning of the Big Bang, but Hoyle and certain of his colleagues were by no means convinced, because they didn't want a beginning for the universe for various reasons, and this was one way they could avoid it. But his theory did die a natural death as new data came along, and the most important of that data was the discovery of the microwave background, in 1964, and then a couple of decades later, the mapping of the tiny ripples in the sky that are the seeds of all the galaxies we see. And this got major headlines when the discovery was announced in 92, for example, front page of the Independent, how the universe began. Notice the word began. We're no longer talking about how this was created. I'll come back to that again. Okay, so this is now accepted. There are many, many popular books on this subject. I just go mention a few for you. So this is a wonderful book, A Short History of Everything. Here's another one in Russian. I'll give you the English version in a moment. The Big Bang. The French have a slightly different take on these things, as they do on most things. Okay. The Creation of the Universe, George Gamow, another beautiful book. He was one of the pioneer fathers of the Big Bang too. A more recent book that describes this in a very popular way. This was Lemaitre's take on things, The Day Without Yesterday, because that was his notion of the beginning also. I wrote a book once called The Big Bang, and another beautiful one is The Runaway Universe, which is the title of this lecture, okay, describing the discovery, which I'm about to tell you about, of the acceleration. And it goes on. This is another beautiful book, The Elegant Universe. I recommend that for popular reading. And then finally, if everything else fails, we have a TV series somehow connected to the Big Bang. Right, okay. So now let's talk about the discovery of the acceleration. So here is the story behind it. One goes back to February the 24th, 1987. And on that day, that night, one saw for the first time ever, actually, in a nearby galaxy, right, with the naked eye, a supernova explosion. Okay, so I mean, several hundred years before, there were faint things that came and went. They were later known to be supernova, but the event in 1997 was magnificent because it was in a nearby galaxy, in the Magellanic Cloud, which is this. A beautiful sight. You can see this in the southern hemisphere as a fuzzy blob with the naked eye, this with the telescope. And so seen, you couldn't miss this if you were looking at this galaxy. So in the center of the galaxy, there's a region where, a few minutes before the explosion, there was nothing, and then suddenly there was a bright star, third or fourth magnitude. That's really bright, that faded away over the course of weeks. This is an exploding star, a supernova, and it made headlines. And the interesting thing for the story of the expanded universe is that the stars that explode like this are essentially perfect bombs, okay? Perfect in the sense they have a certain amount of energy and brightness, and it's like a uniform thing. Everyone is the same if you can choose your supernovae correctly according to the signals you have in its light, in its spectrum, actually. And so the idea is that when this star explodes, it's the remnant of a massive star that's built up lots of from thermonuclear reactions. It's converted into heavy elements. Our sun is made of hydrogen, a tiny bit of helium in the center. In the future, it will turn some of that, it will burn some of that into heavier stuff, and more massive stars do this more efficiently. And then eventually the center forms iron, and iron is a very stable element. You can't burn it anymore, and then the whole thing collapses, and that's what gives you the explosion. Okay, so we believe, and this is like a perfect bomb, it turns out. So that was what a supernova is, and we have all this beautiful data from the nearby one, and now the astronomers began looking far away, and so they found, when they looked at distant galaxies, there was a star that was not there, the night before, and it suddenly appeared out of nowhere, and they could measure from its spectrum, was at the same distance as the galaxy, and it gradually faded away. So this is a supernova almost as bright as an entire galaxy. Okay, it's amazing. One star, and there are 100 billion stars in this galaxy, right? So this star is almost outshining the entire galaxy. And so these have now been charted out in many galaxies, near and far. And here is the result that got astronomers completely astounded. It turned out that the distant ones were simply too faint by about 20%. It's a big factor. Okay, they should not be quite that dim, and they were seen very far away. And the only explanation could be that the universe was larger than you might otherwise think it would be when you look far away, which means it had accelerated. Okay, so here is one of the key discoveries of this. So this was at a moment in the early 90s, actually 1997, that's when the search began in the 90s. And this is Adam Rees, who was a young man at the time. Still is actually, but he was 29 years old. He was on his first postdoctoral fellowship. And at that time, the people looking for supernovae realized they could do cosmology with them, discover the size of the universe, and they wanted just to decide on whether it was actually going to expand or contract in the future by looking far away. That was their goal. And discovering acceleration was a big surprise. And so at the time, there was a large group of astronomers doing this. They had to get observations from all over the world. And it was clear that all the senior people, and it was sort of a group where, the chiefs outnumber the Indians, basically. And so, a lot of chiefs, few people doing the real work. And so they decided very cleverly to let one of the youngest people lead a project to establish how far away the distant supernovae were and do the cosmology. And so he had a piece of luck. He was appointed to be in charge. And then in his notebook, one night in 1997, he was staring at the data and suddenly realized it just made no sense unless there was the equivalent of anti-gravity. This means mass which is negative, which is acceleration, something pushing against the gravity. So that's how it was discovered, okay, and very rapidly, within a matter of weeks or months, his colleagues were convinced. There was a rival team doing the same thing. They were in competition with them to see who could publish first. And both teams, in fact, managed this publication in the same year, 1998. And so what they found was that something weird, and I explain what this in a moment, called dark energy, accelerates the universe. Something is accelerating the universe. And what you measure, the difference between matter, which most of it's invisible, it's mostly dark, and something which has the opposite, it's like anti-gravity, and we call it dark energy. And so this was big headlines at the time, and then a few years later, these guys got the Nobel Prize for this. And so this is Adam Rees, and he shared half the prize with the other leader of his team, and this Saul Perlmutter was the leader of the rival team, and they had the same result. So this was the acceleration discovery. Okay, so let me try to explain what this weird thing is that's accelerating the universe, if I can. Okay, so the basic notion is this, that what Einstein showed us is that I can replace a star by curving space around it. Okay, so that's the essence of general relativity. Space is curved. So you don't think of mass anymore, you just think of space. And so light from a distant star, because of space being curved, its path is bent, okay? And you can think of this as basically a prediction of Einstein's curvature of space. He predicted it. Now, it's true that if I went to the older theory of Newton, I'd still get some slight bending of light because light's got energy and it is affected. But Einstein's theory gave a very, very specific prediction, okay, for this bending, and it was measured in 1919, an eclipse of the sun, and that's how Einstein got famous, etc. So we're convinced he's right. Okay, anyway, so going back to Einstein's famous equation, you now have space being curved, which is gravity, and it's driven by some source of mass and energy as well. Energy has mass. Remember the famous equation E equals mc squared, so energy and mass are equivalent in Einstein's language, and we've learned to live with that for a while. Okay, and in this famous tensor language, I can write the curvature of space and the energy that goes into it. And this was what led Einstein to this paradox. When he applied this equation to cosmology, the universe was collapsing. There was nothing to counter gravity. So what Einstein did in 1917, he said, aha, let me stick in this constant over here, which is going to be anti-gravity, has the opposite sign of gravity, and it will act like, and it will basically stop it. It was just a constant, arbitrary thing in the equations. He felt he had the right to do it. There was no problem with that mathematically, but he regretted it later because it wasn't needed. But it's come back to haunt us because the new thing you can do with this constant is you can stick it on the right-hand side of the equation, a simple transformation. And now it's part of the energy and momentum of the universe, except that it acts like anti-gravity. Normally in relativity, energy and mass, normal energy and mass, they attract. But this is the opposite, it has the opposite effect. And that's the only way so far we have for understanding the acceleration of the universe. This lambda term, as we call it, has a certain value, very small value, but it's enough to dominate over very, very large scales. So it, in fact, has been said to be the greatest force in the universe. And there's one famous story. So the day after the Nobel Prize, Bob Kirshner, who was the head of the team that Adam Rees was part of, the overall head, and in fact, Rees was his PhD student. So Kirshner was interviewed by the New York Times, and the journalist asked him, after the discovery, etc., after the Nobel Prize was announced, Mr. Kirshner, I understand that the greatest force in the universe, what do you think that is? Could that be the dark energy? And Kirshner said, no, it's jealousy. And that's a quote. He was somewhat of a comic, but that was... Okay, so who actually invented dark energy? Again, it's interesting. It was Lemaitre, again, who first talked about it. So this is something from his writings in 1933. The theory of relativity suggests that when we identify gravitational mass and energy, as Einstein said they had to be, then you have to introduce a constant term. You don't have to, but Einstein did. And everything happened as though the energy in the vacuum would be different from zero, okay? And then he says that in order for this to be fair, you have to add a pressure to the density of the energy of the vacuum, and that's the meaning of the cosmological constant, which corresponds to a negative density of the vacuum. So Lemaitre said that in 1933, incredible prescient. Then, we no longer, for 50-odd years, people didn't want to consider it, and then it came back to haunt them. So why did it come back to haunt them? This is essentially why. This is a modern view of Hubble's diagram, okay, in which this actually is speed and distance plotted, but the point is Hubble and Lemaitre studied this tiny region of space at very, very close to us, okay? And by some miracle, they inferred there was expansion, resistor expansion. The errors were huge, but that's what they saw in the data, okay? With enormous uncertainty. But all the modern data continues to incredibly large distances, okay? And the linear law means a uniform expansion. And with the most distant data of all, we're seeing slight deviations from this dashed line. That slight deviation, where the data points lie, indicates distant points are further away than they would be in a uniformly expanding universe. The universe is accelerating, and we can see that as we look far and far away. And this sketch was taken from Lemaitre's notebook in 1928, and you can see these are his models of the universe. There's a big question mark at the beginning, because this is his, time zero, r equals 0. But from then onwards, you have models which accelerate. And this is one of the ones that we're in now, as opposed to one that could, collapse and give us a new crunch in the future. Okay, so it's an amazing story. Let me tell you about some of the ramifications behind this. And so one of them is this question of, was there something, what is the beginning? Was there something there or was there nothing? Did we begin from nothing or something, okay? And this has excited both philosophers and scientists. One quote from Stephen Hawking, it said there's no such thing as a free lunch, but the universe is the ultimate free lunch. And I'll explain to you where that came from. It comes from the theory of inflation, which gives you this dramatic expansion of the universe from a very small size. And this issue has been debated more and more. Hawking wrote also that maybe that one does need something more than nothing, okay? And this is a way of his saying that in beautiful words. What is it that breathes fire into the equations and makes the universe for them to describe? Why does the universe go to all the bother of existing? The universe would be completely self-contained and not affected by anything outside itself. It would neither be created or destroyed, it would just be, okay? And all of this is basically saying that, things really did begin with physics, okay? And Lemaitre was a pioneer of this way of thinking. And so he says this, for example, the radius of the space grows with time. It's unavoidable that precedently it was smaller and smaller. A naught value of the radius induces a physical beginning and does not deserve any more the title of creation out of nothing. So, as physicists, we're then entitled to discuss the beginning of the universe, but for Lemaitre, it was interesting. There was a very interesting division. And let me just illustrate that for you with his influence, basically, on, he was a priest, as I said, and his influence on the church, in fact. He said that everyone who believes in a supreme being believes also that God is essentially hidden and may be glad to see how present physics provides a veil hiding the creation. So Lemaitre was able to think in two directions, a physicist and a theologian, and he certainly convinced the powers that be in the Catholic Church. We have John Paul, no conflict between faith and theory of evolution. Francis, the theories of evolution and the Big Bang are real, and God is not a magician with a magic wand. Okay, so that's a very interesting, way of presenting the context of the Big Bang in our current society. But now let me return to the physics, okay? And I'm going to show you with this one new thing, dramatic new thing, which is very important for the beginning, and that's what we call the theory of inflation. So I apologize for the equations, but what you have to realize is that what I'm showing is the acceleration of the universe, and basically acceleration must be positive, it must be increasing. And if I put normal matter into this, I get something negative, which means it's decelerating. That was the standard view before the discovery. And so the way scientists move around this is they add a new physics term, okay? Let me not even begin to explain what that is. We call it a field of energy. And if it changes very, very slowly, then you can arrange for the pressure to be predominantly negative, okay? And that means these terms here are zero. And if it's very negative, then you get a very bizarre thing that happens, you get an inflation. So this, then, we just look at this, then this says the universe began from something very, very small, and there was a period where it grew exponentially rapidly, okay? And then this was what we see in the microwave background, way back a few 100,000 years after the Big Bang. Then billions of years elapse, and now here we are over here looking back, seeing all the galaxies. And then finally, as we look back recently, we're beginning to see acceleration again. So it's almost as though the story is repeating itself, okay? So we had exponential acceleration for a brief period then, at the beginning. We have theories of that introducing a weird new field, but the same thing may be happening now. Maybe it's the same story repeating itself, except the energies now are much, much lower. And that has created a bit of a problem for many of my colleagues to understand. So before I tell you what that problem is, let me tell you why we have faith in this amazing story at the beginning, whereby the universe began some incredibly tiny and incredibly high mass that could be seen by any hypothetical observer to something huge. And so why the theory behind that is called the inflation theory. And it was developed in the 1980s by these two gentlemen. And it predicts several things, okay? It predicts why the universe is as big as it is. It predicts why space is so close to being what Euclid said it would be, very close. Things, gravity and expansion sort of balance out and make it exactly flat. And it predicts the tiny seeds from which structure was made. And so the amazing story is that this inflation theory, you can start off with some random universe and then things expand and then enormously, and it becomes locally, very close to Euclidean and enormous compared to what it was before. That's sort of a cartoon. And we know all of this from looking at this microwave background, which is all described by simple 6 numbers. All these data points are on this curve, just 6 numbers. It's a simple theory, which is why many physicists trust it, okay? That doesn't mean it's true, but they trust it. And so it predicts 5 different things, these fluctuations, the fact that they give you some sort of coherence, meaning that you had a beginning, the fact that there's a certain curve which goes through them, can be explained simply by the theory, and then 2 things which they should be totally random, that's seen, and finally a great prediction which has not been seen yet, that there should be tiny ripples in space imprint on the fluctuations, which you could see in the future by measuring tiny effects due to the polarization of the radiation. That's not been done yet. In fact, over the next 10 years, it's one of the major goals of cosmologists throughout the world to look for this final prediction. If they find it, then they will feel confident they've verified this theory of inflation to high precision. You can be completely certain anything is right, but they'll be much more confident. So why is this such a beautiful theory? This is why I find it so appealing. So here the universe is expanding, essentially at the speed of light. As time goes on, you see more and more of the universe. And this corresponds to the physical mass that's contained inside a galaxy such as ours. Now, because a galaxy has mass, it can't quite expand as the matter that will in the future make a galaxy can't expand quite as fast as the speed of light. So it's a little bit slower, which means if I track back in time, this represents the stuff in our Milky Way, for example. If I track back in time, once it was larger than the distance light can travel. We call that the horizon. That is very, very bad. It means for cosmologists you have to put in something at the beginning, which one hates to do. It says there are initial conditions of the universe which we don't understand, we put in by hand. We don't like that. But the beauty of inflation is because it has this incredible exponential effect here, you can then explain things as being causal and they can come from the quantum theory or whatever. So that's beautiful. That's another reason why you believe in inflation. But we're seeing the something similar happening now, okay, as the universe is beginning to accelerate. And again, physicists are very unhappy. They're willing to accept this. This could be explained by energies which are very, very high, driving this incredible explosion at the beginning. But today, energies are lower. Things have cooled down. It's harder to imagine. And so here is a pie diagram which tells you about this weird dark energy, which dominates the energy of the universe, really, and is this force which is accelerating it. And you have a prediction which comes from physics. You don't have to read any of the numbers, but the prediction from physics is this number, that it should be this big. And what astronomers measure is a much, much smaller number. That's the cosmological constant that's doing this acceleration. So here's what you expect if particle physics were controlling this. It's completely different. And this has been called the worst prediction in all of physics. Okay, so now you can take this as just a fact. The universe has this constant in, but not everyone is happy with this. In fact, this is a quote from one of the most famous of the so-called string theorists in an interview. Dr. Witten allowed dark energy might have transformed this from a vice into a virtue, a way to generate universes where you can find any cosmological constant you want. We just live in one where life is possible, which is fish only live in water. That means in all these other universes, which inflation theory can predict, there are versions that predict this, each one is a universe. And in one of these universes, here we are, where, that constant term is small enough to allow life to exist. If it were too large, it would rip us apart. That's the problem, because things would just accelerate to hell, right? And so many of these other places are no good for life. Maybe they're too cold or too hot. It's a bit like the Goldilocks problem, but this one is just right. And if you have enough of them, then you can explain why it's so incredibly improbable. Okay. Now, not everybody likes this. Here's a quote from another colleague. And this we call the multiverse, because multiverses can explain anything. The answer is likely to be there is none. Okay, so we have discordant views in the community of cosmology. Some say this is a physics explanation. Others say that it's not. And it's interesting to go back to history. So let me show you one statement in a different context about another cosmology. The authors of this new cosmology are primarily concerned about the great difficulty which must face all systems that contemplate a changing universe, namely how we can see to have begun. They're not content to leave this question unanswered until further knowledge comes. All problems must be solved now. Now, for some reason are they content disposed that at some period in the distant past something happened that does not continually happen now. Okay, and so on. Okay. Now, the interesting thing, and if we must really answer all questions immediately, is their solution in fact more intellectually satisfying than that of a special creation? So this is a comment that could apply equally well to the multiverse, but it was written in 1951 by Herbert Dingle, referring to the steady state theory. Okay, so in some sense, we may not have advanced so far. We have a theory now also which is precious little evidence. With the steady state theory, the evidence came later, okay, and disproved it. We're waiting for evidence, and it may be impossible by definition to get them. Why so? Because if there is such a multiverse, by definition, you can't see outside our own universe. That's the problem that we have. And so, to some extent, one is wrestling with philosophical issues. And it may be the only real solution is to wait for some new Einstein to arise, and then this new theorist would finally solve the problem of quantum gravity, which is the basis of it all. We don't have a theory, so it's the quantum theory and gravity. That question mark at the beginning of the universe is a question mark for theory, and that if we ever had a good theory, maybe that would explain the low value of the dark energy, of this cosmological constant. Okay, so let me make a prediction now from the theory that we have of the measurements of the acceleration. What does that predict for the future? And that's an interesting story because, so here we have, this is a sketch of how far we can see with our biggest telescopes, some 15 billion light years from us, okay? Now imagine that the universe is really accelerating, okay? So before acceleration, if we had an orbit expanding Big Bang, then as time went on, we'd see more and more galaxies. We would have lots of new friends to make in the distant future. But everything is now accelerating away from us, okay? So interestingly enough, in about 140 billion years' time, this is going to be our horizon. Just our Milky Way, everything else, and maybe our nearest galaxy, Andromeda, everything else will have accelerated outside the horizon. Okay. Now that's a long time, 140 billion years. You may say it's totally irrelevant. It probably is. But there was one discovery last week which gives me some hope that there may be astronomers around to measure this. So maybe you saw this on the news, but there is a dwarf star, not very far away, a mere 29 light years from us, around which there are a number of habitable planets like the Earth, rocky planets, possibly with atmospheres, possibly with water. We don't know yet. Okay. But the interesting thing is the lifetime of this star, since it's less than a quarter of the mass of the sun, is 1 trillion years. So if and it turns out that most of the stars in the galaxy are dwarf stars, so most of the planets in the Milky Way, habitable planets, are almost certainly around very long-lived stars. So, the sun will only last another 5 billion years, then the Earth will be burnt up as the sun becomes a red giant or whatever. So we'll have, presumably any civilization left at that point will have left for greener territory elsewhere. But in this case, this is a sketch of what it might be on one of these, and these, of course, are artist images of these Earth-like habitable planets. So there are planets there. So if the universe really is accelerating, there may well be something totally different for the astronomers to absorb in this distant future. Okay, so in the meantime, if I now go to a slightly shorter timescale and talk about the next 5 or 10 years, so this is basically the future for learning more about dark energy. Clearly, we measure a certain rate of acceleration, but maybe that is changing slightly, right? If we could measure with more precision, maybe we'd see the universe slowing down again. As we look further and further away. So the race is on now to build bigger and better telescopes to measure with more precision the acceleration of the universe. And these are some of the amazing projects. We have a telescope in space to be launched at the end of next year called Euclid. We have a telescope under construction. This is an 8-meter telescope to survey the sky again and again and again, looking for traces of that could understand the acceleration better. And finally, 2 enormous telescopes, a 30-meter one planned in the US, and a 40-meter one planned and under construction already by the European Southern Observatory in the Atacama Desert, high in the Atacama Desert in Chile. And then various space projects, and there's one project on the South Pole also, which is designed to measure cosmology with incredible accuracy. So things are, booming in cosmology. The fact that we don't understand the dark energy has not deterred my colleagues from building bigger and better experiments. In fact, it's encouraged them actually to the fact that given that we have some paradox out there in the universe, we better understand it better. If the dark energy really, or the acceleration is different from what it appears to be so far, if it's observed to change as you get further away, that would help us understand what the physics is behind that acceleration and enable us to come to grips with what is really going on far, far away in the universe, and incidentally, what our future might be. So, thank you.